line at theta equal to, this is positive theta. At this point, whatever motion it has in certain direction, so suppose this is theta naught and omega in this direction. So in the other direction, the body will have the same motion, right? In minus theta direction here, this will move with theta naught and this will omega naught. So this will be kind of a symmetry. Is this clear?
Yes, sir.
Yes, sir.
Okay.
Yes.
So this will have kind of a symmetric motion about the, this is the line of symmetry. So this will be perfectly symmetric with respect to this vertical line, which is the equilibrium position of the pendulum. There is another symmetry which we will note from there, is that from this equation, that is, if you substitute t by minus t, this time I changed. Okay, I changed the time. So in that case, what will happen? d2 theta dt square if I change to minus t and d2 theta dt square, another differentiation with respect to time, so minus of d dt of minus d theta dt, which becomes d2 theta dt square. So this becomes, actually I should not say equal to, this becomes d2. So this does not change, theta double dot does not change. Sin theta I have not changed, I have changed only the time. So if you change the time from negative time, positive time to negative time, you see the equation of motion does not change. Of course, d theta, so what I need here is that, so this is what we have, but the initial condition, what we have, this initial condition, theta at time t equal to 0, this was theta naught. Of course, there is no time derivative involved. Theta, if you change time t equal to negative, then it becomes also t equal to 0. But theta dot at t equal to 0, okay, theta dot now it changes to minus theta dot. As I said that because time is changing, so to negative time, so therefore derivative, first derivative with respect to time, this becomes negative because t is changed to minus t. If you consider, let us say tau equal to minus t and dd tau, this becomes minus dd t. So that is what I am doing throughout here, that when we mean that time is changed to negative time. Okay. So if you consider another variable tau, which is minus t, then derivative with respect to time is changes the sign. So here you see that the initial condition now has to be in this particular frame. Here theta, so this is time, negative time. I am considering theta dot t equal to 0 is minus omega naught. So what it means that if you consider either time t positive or negative, equation of motion does not change. Initial condition changes, only its value of the velocity, of the angular velocity here. Angular velocity negative means that actually the direction of the velocity is changed. The magnitude is remaining same, but the direction is changed. So it means that if you have any vibratory system in this particular situation, this bob is moving there, and
Sir, I have one doubt.
yes.
Sir, how the time is becoming negative?
No, I'm just taking time negative, means that instead of using the motion of the clock here, then using the clock, I am considering clock backwards in time. That means it's rewinding. What I say is that this one, what I mean is that I'll have, if you plot theta t versus t, here in this case, you'll get one particular signal, right? The response will be looking something like this. It starts from theta naught, so something like this it will happen. Negative t, so this will be positive t. It goes in the direction. Here in this direction, this is negative t. What I say is that the negative t, everything will remain same. Now theta remains same here. Velocity in this direction it was initially it was zero velocity. So in the negative t direction also this will be like that. So it does not matter whether we use the time forward or backward. This is actually this kind of time symmetry has some implication. I'll tell you later when this symmetry is broken if you have damping in present. So there will be damping. I'll talk about this damping. So this particular symmetry in time does not exist. So without this damping, the body looks same. So for example, there is pendulum dangling. Okay, so it's a to and fro motion of this pendulum. Now you record the motion. Fine. You see, and if you say record the motion, so you see that if the time, so what? Let me tell. If the time has a possible, if it was possible to take the time backward, then the motion of the pendulum would not have changed. So you get what I mean? That if this is a miracle, now suppose a miracle happens that everything is going backward, okay, backward in time. So the motion of the pendulum, which is what you see in the forward time movement, it remains the same in the backward time movement. So that's what I mean. That this comes mathematically. I mean, this symmetry is actually coming just completely in terms of mathematical language. Okay, nothing else. If you replace t by minus t, the equation of motion, everything remains same. So well, you need not think too much on this one because what I am considering and asking you to do is kind of thinking of an improbable situation or impossible situation as time is moving backward. But what I mean is that the solution of the system will be just if this is like this, it can be extended backward like that. Okay, so you cannot differentiate this motion from that motion. Okay. Well, the negative time also has some usefulness if you consider shifting in time, but that is different thing. I will not consider in this class. So, what from today's lecture, what we have learned is that this vibratory system requires two minimum things. One is that a restoring force field, and another is the inertia. Yeah. Any doubt, please? Okay, inertia and the restoring force field. So therefore, restoring force and inertia. Now the prototype in the mechanical engineering, the prototype of vibration, we take a spring and a mass. Okay, because this element, physical object is capable of giving a restoring force. Okay, as you are always thinking that vibration always means that a spring and a mass. Of course, it's a prototype example of vibration. And there is a similar term called oscillation. Vibration and oscillation, what is the difference between vibration and oscillation? They are same, right? Or there is any difference? Vibration and oscillation are the same?
The oscillation has a fixed time period.
Yeah?
The
Oscillation has a fixed time period.
Fixed time period. Unless the vibration is random or aperiodic, all the vibratory system will have fixed time period. So oscillation is actually similar to vibration, but the word vibration we reserve for mechanical system. Oscillations is also kind of a to and fro motion, but it may not be motion of a mechanical system, right? Motion of a physical motion of a particle. So there may be motion like the motion of the charge. Okay, in electrical engineering, they study the oscillatory system, and this oscillatory system, they have So this is the analog of this oscillation. The stiffness is analogous to the capacitance, and the mass is actually analogous to the inductance of the circuit. Okay, so this is in the electrical system. In the chemical engineering, of course, there will be chemical oscillations. It is very rare to find out oscillatory chemical systems, but in also there will be chemical oscillations. That is, there is a back and forth, to and fro, or back and forth production of the product, reaction product. So sometimes if you consider two mixtures, let's say there is a reaction which I do not remember, it's a Belousov-Jabotinsky's reaction, but this is kind of iodine, etc. All these are mixed, and people can see a periodic color change. That means this product is actually appearing, then disappearing, then appearing, and so on. So this is a repeated production or oscillatory production of the product, and this is known as a chemical oscillation. So oscillation is a very general term, but the mechanical oscillation we reserve it for the mechanical system. The vibration. So sorry, the vibration we only consider the mechanical system. So we do not say vibration of electrical circuit, but electrical oscillation is a very usual terminology in electrical engineering. Okay, oscillation in the electric field. So electrical oscillation is there, but for the mechanical system, we reserve the term mechanical vibration. We do not consider mechanical oscillation. Normally, we say that mechanical vibration. Vibration is a to and fro motion, where motion is actually a physical movement of the physical body. Okay. So these are the things, and this is kind of a prototype example of mechanically vibrating system. There is a spring which signifies the restoring force, the presence of restoring force, and the mass, which is actually the inertia, which gives the inertia. But as I said, and as I showed you, that there need not be a physical spring present, or the mass needs not be in this particular rigid body mass. I'll give you one example. Maybe this problem I'll solve later on. There, for example, there is a container, maybe unequal area. So, and this is filled with water. Okay, it's not completely, partially filled with water or liquid. Now, if you see that if you disturb it, that means if you somehow disturb this one, so let the water level go this side because of incompressible nature of this water, this level will go below. So then again it will start oscillating. Okay, you will see that if you can do this experiment yourself, it will just oscillate. That means it will move back and forth. Okay, so this oscillation, of course, you understand that there is a restoring force field. What is this restoring force field? Again, this gravity, but of course fluid pressure will come, but this can be related to the gravity. But the motion, the inertia is now not the concentrated inertia, but the inertia kind of distributed inertia. So this is also capable of doing a mechanical vibration. So there is a maybe fluid oscillation, we can better name it, but this is one example of vibration. And there you understand, you can name the restoring force field and the inertia force field. And this is not like there is no physical spring present or a lumped mass present. So spring and lumped mass, this simplifies our analysis, and this becomes so common in mechanical engineering that by vibration we always mean that there has to be a spring and a mass. But this is not necessarily so. We'll have very complicated systems which will of course do the same as a single mass and spring system, but it will look a very complicated one. Okay, you can think of this one. Suppose there is a there is this circular trough is there, so it's a path, and a ball is there. This ball may have some mass can be cut out of it. Okay, they may be eccentrically hollowed. So this actually is just unbalanced. And when you leave this, then you'll see that this is actually capable of oscillating. It is very much like a simple pendulum because the restoring force field is gravitational field. But now see the mass will be a little different than what you have your lumped mass. We can analyze this situation and we'll do definitely analyze it. But this is also capable of vibration and there is no physical spring and no kind of lumped mass in that sense. Of course, what we require is that there is no slip at this point. So at this point, this is pure rolling. Okay. It will be same as a single vibratory system. We can represent the mass and the spring. So it is not needed, not in general required that the mass and the spring will have some value. So what we name this is a mass. Actually, this mass is better to call this as equivalent mass because there need not be any physical mass like that in the system, just like in the fluid oscillating system which I have drawn earlier. So this will be equivalent mass, and there may be equivalent spring stiffness. So the spring stiffness is actually representative of the restoring force field, and not only that, also can, but we can find out the equivalent stiffness of that. Okay. So I think we should stop here, at least the lecture part. Now let me tell how do we proceed. We have a class. So first of all, do you have any doubt in whatever I have told today?
How to calculate equivalent mass?
Yes.
How to calculate equivalent mass? We have
how to calculate that depends upon the system. That depends upon the system. See, that depends upon exactly on the system. Like here, the pendulum. Of course, in the pendulum, actually we had a very funny situation, and that's why I took this example. The mass is not present in the equation of motion. The equation of motion, you didn't have any mass. Theta double dot plus g by L sine theta equal to 0. So there is no mass present there. Okay. So that is because the restoring force is also proportional to the mass, and that mass cancels out. But what is important is that the effect of the inertia is not only in mass, but in the mass times acceleration. So this part is there. Interestingly, in this expression, there is no mass appearing. So pendulum bob, the motion, whatever this bob executes, this is independent of its mass. Okay. So here you can consider the mass to be, so if you write down now at this stage, I'll do that. So theta double say theta, I'll consider very small compared to 1, and then sine theta will be approximated as theta. Because sine theta exactly sine to the power 5 by 5 factorial and so on. So when theta tends to, so sine theta, limit theta tends to 0, limit theta tends to 0, sine theta by theta tends to 1. Okay, because other terms becomes, this is 1 minus theta cube by all this stuff, so therefore sine theta becomes theta, and in your equation we will have theta double dot plus g by L theta approximately, this is equal to 0. Now here this is in the form mx double dot plus k. So anything you can take inertia, the mass m equivalent you can consider 1, and k equivalent you can consider g by L, or you can consider m equivalent as any mass and k equivalent mg by L. So whatever you consider, so what it means that this time the standard equation of motion mx double dot plus kx equals 0. This is the equation of motion of the spring mass member system, and we can say which the coefficient of acceleration term. This we normally take that as equivalent mass, and that coefficient of x, that is the displacement. Here theta, we take this as the equivalent spring stiffness. Okay. But that depends upon which system you take, because equivalent means that we are taking the equivalent of a given system. We are trying to find out an equivalent system consisting of a spring and the mass. So what will be the mass and the stiffness for which the equation of motion of that particular spring mass system will be just the same as the original equation. So this is how we find out the equivalent mass and the equivalent stiffness. So what I wanted to say is that the vibratory system does not always require, does not require spring, and systems which will have no spring, physical spring, may execute the vibration as the pendulum did. Because what will happen? The spring is nothing but an agent to give the restoring force. Here in this case, gravitational force field was the same restoring force field. So it did effectively did the purpose of a spring. Understand? Clear?
Okay.
Yes, sir.
Yes, sir.
So this class, so we'll have the lectures on Monday from 11. Wednesday, Monday 10 to 11, Wednesday 10. This I have got from ERP. So in your ERP system, it is showing the same thing, I suppose. So this is the timetable. Okay. And one class will have this Wednesday class will be of 2 hours. Okay. I may not take both the hours for lecture. So 1 hour will reserve for problem solving. And so tutorial. So 1 hour will be for the tutorial.